of the conference. We've saved, no, I mustn't say we've saved the best till last because we've had a wonderful conference. So, but I do believe that this is hot off the press. And so our last speaker is John Morgan, JP Morgan, from Virginia Tech, and he's talking about efficiency, optimality, and differential treatment interest.
Thanks, Angela. And I wish it was hot off the press, but it's not even to the press yet. So, thanks to the organizers for a memorable 4 weeks, and to the speakers the last couple of days. I say when you're the last speaker, what happens is, come Wednesday morning, you wake up and say, "Oh my God, I've got to make a talk." And so, the last couple of days, I really haven't been here, and I apologize to all the speakers who I missed. So here are the basics for the talk. Talking about a simple situation that we have in a comparative experiment. V is the number of treatments. We have some experimental units, Vn of those. Experiment may be blocked or unblocked, but it's going to be a bottom stratum analysis, so if it's blocked, I guess you can think of the blocks as fixed effects. For convenience, I'll rarely write a sigma square, so you can just assume it to be 1. And each design D, there's an information matrix, and I'll write that as C sub D. Okay? So the purpose here is to incorporate what I call asymmetric treatment interest, or unequal interest in treatments, in building optimality assessments of designs. And to get an idea of what needs to be done, I'll just very briefly sketch the standard optimality theory for these sorts of situations. Let phi be some optimality measure, so it's just a map from the information matrix to the real line, satisfying typically 3 conditions. 1, it's convex, matrix convex. Number 2, it preserves the non-negative definite ordering of matrices. And number 3, it's permutation invariant. And it's that third one that we're really going to be trying to get to. And of course, included here are the popular measures like A, D, and E. So the permutation invariance, what does it say? Bring it right up there. So any permutation matrix P I apply to the information matrix. I take phi of that, and I get the same thing as if I hadn't permuted at all. Well, this really is saying that any optimality evaluation is unaffected by treatment interchange. And if you have unequal interest in the treatments, that's not a tenable thing to do. So interchanging treatments having different interests should produce different values of any optimality measure. It's pretty clear what we're going to have to do. If we're going to have asymmetric treatment interest, then that full permutation invariance is much too strong. So we need measures phi such that the same relationship right here holds only for the treatment permutations that are allowable by our interest. We're still going to want the convexity. We're still going to want the non-negative definite ordering. And however we implement this, we want to do it in a meaningful and a transparent way. So a couple of examples just to get the idea of where all this comes from, and a very natural one, it's been talked about elsewhere in the conference, is test treatments versus the control treatment. And here I'll just write it as the first treatment is the control, and then we have V minus 1 other treatments. There are test treatments, and there is clearly an asymmetry of interest between the control and the test treatments. So the control should not be interchangeable with the other ones for the purpose of design evaluation. And how do you do this? Well, I'm going to show you the standard way it gets done, which is this. We just form the elementary contrast between tau 1, the effect of the control treatment, and the V minus 1 test treatments, and we'd get the information matrix for that. And so there's the matrix of coefficients for those contrasts. This is the information matrix that you end up with. And then with that information matrix, you apply standard optimality theory. Okay? So this is now V minus 1 by V minus 1 rather than V by V. But notice what this is saying. This is saying that you have equal and dominating interest in those pairwise comparisons right there. And so one of my criticisms is that that might not really be the case for many experiments where we have a control and a bunch of test treatments. That's all we want to look at. And so why should we base our optimality measure on just that set of contrast right there? So that's what this slide says. Shortcomings. In some experiments, there's also serious interest in comparing the test treatments to one another. These comparisons play only a secondary role in the standard approach. And indeed, there are experiments in which comparisons with control expected to be large controls, simply there is a check. And so that really the greater emphasis is on comparing the test treatments with one another. And yet you have a control and you have test treatments. So we'd like an optimality approach that allows for the relative interest in the two types of contrast to be accounted for. Okay? That's our first example. Here's the second one. It's kind of an example, kind of a suggestion of where to go. I call this selective replication. So let Ri be the replication assigned to treatment I. Well, in an unblocked experiment or completely randomized design, of course, we all know the means are estimated with variances sigma squared over Ri, right? And so the relative information in an unblocked design is just Ri to Rj for various treatments. So here would be a very simple strategy. If you have twice as much interest in treatment 1 as you have in treatment 2, then assign twice the replications to treatment 1 to treatment 2. And of course, all your information ratios, if you can do this properly for all your treatments, are going to reflect exactly what your relative interest is. So I'll say with this strategy, a CRD provides perfect information. Perfect in a sense of accounting for the relative treatment interest, right? So the relative information gained on each treatment is exactly that desired, provided, of course, the integers work out because it is an integer problem. This perfect information is reflected in the non-zero eigenvalues of this matrix right here. And what is this? Well, that's the information matrix for the completely randomized design. And dr just means the diagonal matrix of the replications. And we've taken the square root of that, inverted it, multiplied it front and back, and we'll find out whatever the replications are, all those eigenvalues are always equal to 1. Okay? Now, let's look at a block design, and let's do the same operation to its information using its replicates. So the same relative interest is exactly preserved in the block design if its non-zero eigenvalues are all equal. Remember the previous all 1. If these are all equal, and it turns out they have to be less than or equal to 1, then relatively speaking, we have exactly the same relative information in this block design as we would have had in the completely randomized design with the same replications. In fact, most people here are going to know this because it's been talked about quite a bit at this conference. Do this operation to any design. There's your information matrix in the middle, and its eigenvalues are called the efficiency factors. And there's been a notion floating around for a number of years called efficiency balance, which just says that all the efficiency factors, except for, of course, one of them is 0, v minus 1 efficiency factors are all equal. Okay? So one of the points of all this is that efficiency factors can be thought of as measuring adherence to assigned treatment interest as specified by selection of the replication numbers R1, R2, up through RV. Now, I'm not saying that's the only thing they do. Everybody here knows they do other things as well. But that's one way of thinking of efficiency factors. And I think that raises a couple of interesting questions. First of which is, does efficiency balance provide a good design in an optimality sense, respecting the assigned relative interest in the treatments? And the second is, and I put this down because I've seen this in a few papers that have appeared over roughly the last 15 years. Can functions of efficiency factors be used as optimality measures incorporating relative treatment interest? All right, so we'll be coming back to these things. Now we're ready to get our setup with our idea. And you see our V treatments displayed there, and what we're going to do is we're going to associate a weight with each one. So W1 through WV. Each weight is positive, and the sum of the weights is 1. And the point of the weights is these are supposed to specify your relative interest. So if W1 is 2 times W2, you're putting twice as much emphasis on treatment 1 as on treatment 2. Now we can define a way of measuring optimality taking into account the weights that we've applied to the treatments. And so for any conventional criterion phi, as defined on the second or third slide earlier, we're going to define a weighted criterion, phi sub w, by phi sub w of CD equals phi of this matrix. So this W is just the diagonal matrix of the weights. All right, so you see what's happened there. This looks like what was being done in the efficiency balance situation, but we're using weights here. We're not using the replications. We're using the weights that talk about our relative interest in the treatments. Another way of saying this, which I like a little bit better, is just go ahead and define this matrix to be what we'll call a weighted information matrix. And so CD with a W stuck on there for the weights. Call that the weighted information matrix. Then we can take any regular phi and define a weighted criterion as weighted criterion of CD equals phi of weighted information matrix. Okay? Now, these, of course, are definitions, and we can see what implications are for standard criterion. Let the positive eigenvalues of the weighted information matrix be called thetas. Then, of course, we could define weighted A, right? As just the average of the inverses of the eigenvalues of the weighted matrix. We could define weighted E as 1 over the smallest positive eigenvalue of the weighted information matrix. We can define weighted D as the product of 1 over the theta i's. All right, so we can define all of these things, but definitions are easy. The question here is, are they meaningful for the problem we want to talk about? So I want to get at an understanding of how applying weights to an information matrix induces weights on variances of treatment contrast and how those things are really being taken into account when we do one of those weighted measures of optimality. So towards the definition of weighted variance, we'll look at the spectral decomposition of the weighted information matrix. So here you've already seen the theta i's as the eigenvalues and fi's are corresponding eigenvectors. I put the 0 in here as well. That's the 0 eigenvalue because we're going to need to look at the F0 that goes with it. In fact, here's the F0. So if that's the vector of weights, the little w, then F0 is the square root of the vector of weights. Okay? So let's now define some new vectors. Call these guys Li by taking eigenvectors from the weighted information matrix and pre-multiplying them now by the square root of the diagonal weight matrix. Then it's pretty easy to show that each Li makes a contrast, that the Li's are normed with respect to the weights, and that the Li's are orthogonal with respect to the weights. And these properties make it very easy to calculate variances and covariances for these Li transpose tau contrast. Variance of Li transpose tau hat is just 1 over the corresponding eigenvalue. And covariance of two such contrasts is always 0. Okay? So since these contrasts that have been derived from these eigenvectors have such nice properties, seem to be kind of special, let's give them a special name. We'll call these the weighted basic contrast for the design. And it's easy to see that they are a basis for the space of all contrast, and as we already noted, they're normalized with respect to weights. In fact, we say these contrasts are weighted orthogonal because of, well, either one of those properties there, I guess. Okay? And now let's put all these contrast vectors together in a matrix called L. So L, of course, is nothing but W1/2 times the matrix of the eigenvectors, leaving out that F0 that went with the 0 eigenvalue. Because they are basis, any contrast could be written as a linear combination of the basis. And so now let's look at an arbitrary contrast, C transpose tau. It's a linear combination of the weighted basic contrast. So there's some vector Q such that C transpose tau equals Q transpose L transpose tau. And using the weighted basic contrast, we can work out the variance of C transpose tau hat. And it comes out to be summation Qi squared over theta I. All right? Now that variance, as you can see, is clearly a convex combination of the 1 over theta I if Q transpose Q is equal to 1. All right, if that Q had been normed. Well, let's look what it takes to get the Q to be normed. It's easy to see that L transpose W inverse L is an identity matrix, so Q transpose Q, which expands like this, is nothing but C transpose W inverse C. All right, remember, W is the diagonal weight matrix. So the variance, this is now a definition, the variance for contrast in the weighted sense is the ordinary variance of the contrast, right here, divided by this weighting, which norms it in the space relative to those weighted basic contrasts. Right? Multiplier right here is called the weight of the contrast. So there it is up the top again. A few observations. One, the weighted basic contrast all have weight 1, right? Because when you put L's in here, you get 1. In the unweighted case, what's the unweighted case? It'd be all the weights are equal, and since they sum to 1, they all equal 1 over V. And you just plug that in, and you find out that this translates in the weighted case to looking at just a regular old normalized variance of a normalized contrast, except for every time a little constant pops out front, and that has to do with how we chose the constraint on the weights. We put sum equals 1. If we'd done something else, we could have got rid of that, but it seemed much more natural to say sum of the weights equals 1. Optimality criteria that are functions of the theta i's, eigenvalues of the weighted information matrix, through their inverses are doing what? They are evaluating weighted variances. With that definition right there. Okay, so now let's take a closer look at the weighted versions of conventional optimality criteria and see what they say. I'm going to pay a particular attention to what we call the two-weight problem. So now rather than arbitrary W1 through WV, I'll just call them W1 and W2. W1 is the weight assigned to each of the first V1 treatments, and W2 is the weight assigned to the remaining V2 treatments. And so still they add up to 1. That V1 plus V2, of course, is V. We'll just take V1 less than or equal to V2. And if we put V1 equal to 1 in this situation, what are we talking about? We're talking about test treatment versus control. We have one weight on one treatment, everybody else is considered equally weighted. So what is weighted E all about? Well, I'm just going to write down some results here. The first is the weighted E value is the largest weighted variance over all treatment contrast. So accounting for the weights of how important you're saying each contrast is, if you want to minimize your worst case, what you should use is weighted E. And by the way, you might want to think about each of these things. Just say to yourself, well, what would it be if I had equal weights? And it always turns out to be exactly what it should be. In this case, it's maximal variance of a treatment contrast in the normalized space. Okay? If we partition the information matrix according to the weight groups, so this is V1 by V1, this is V2 by V2, and we look at 1 over the E weighted value and take the limit. So as W1 goes to 1 over V1, I probably should have written here actually W2 goes to 0. It's putting all the weight on the first group. Then so long as V1 is bigger than 1, this thing will give you the smallest positive eigenvalue of this matrix, which in fact is the adjusted information matrix for estimating contrast just in group 1. So it's giving you exactly what it should give you. It's a little trickier when you only have 1 in the group that you're throwing all the weight on, because you let all the weight go to 1 on one treatment, you got no contrast left, right? And yet it can be done, and that's the next result here. Actually, you end up multiplying by W2 and then taking the same limit. Now W1 is going to 1 because it's only one treatment there. And this gives the smallest positive eigenvalue of this matrix, which in fact is the one we wrote early in the talk as the information matrix for the standard test treatment versus control situation. One of the things I want to point out here is that part of what this is saying, and all the other criteria say the same thing, is that the standard take on test treatment versus control is the limit as W1 goes to 1 of what's being done here. All right? It's saying put all your emphasis on the control treatment. But if you want to do less than that, then you should use some W1 less than 1. We'll skip that one. About the weighted A, and we also talk about weighted MV. A couple of results. The weighted A value is the average of the weighted variances of any V-1 weighted orthogonal contrast. Again, put equal weights there. It's a well-known result. The weighted A can be written as a sum of weighted pairwise variances. Put equal weights there. It's a standard known result. But one thing curious here, this WI, WJ is not the weight, not the weighted not the weight that goes with the variance of a pairwise contrast. It's clearly a weight. If we want to see the weight that goes with a pairwise contrast, it's this thing right here. All right, so this little bit disappears in that expression for whatever reason. So this is a legitimate thing to do, and so is this. So if we want to look at just pairwise variances, we may think of minimizing the worst weighted pairwise variance, and that would give you the MVW criterion right there. Okay? And if you do the asymptotics, letting one group have weight 0, another group get all the weight, then for both of these two, everything works out very nicely. So just what you think it would be. Weighted D, this is a different cat. If D1 is D better than D2, then D1 is D weighted better than D2, no matter what your choice of weights. What does that say? It says the D criterion does not distinguish changes in your interest on different contrast, and so there's no need for us to look at anything called weighted D any further. About that permutation and variance. With this definition of a weighted information matrix, what we find is exactly what we'd want to find. That if we let script P sub W be the set of permutations that preserve the weight vector, then we get permutation and variance in the optimality criterion for every design if and only if we have a permutation matrix that preserves the weight vector. All right. And this has some very strong implications because now if we average, which is a typical sort of thing to do, symmetrize over a set of permutations, and we use these that are allowed, let's get a matrix CD bar, which is the average over the allowed permutations. Then using convexity, we get the weighted evaluation of CD bar is less than or equal to the weighted evaluation of the design that we started with. And what do we get? Well, if we had the 2-weight problem, we were permuting everything over group 1 and everything over group 2, we get an information matrix that looks like this for the CD bar. All right, and there's more than 2 groups. It's just repeating that pattern for more groups. And so these generalized group divisible designs become the target for optimality investigations when we're talking about this weighted optimality. Now, if you're doing this in the unweighted case, what would happen? Well, you do all permutations, you get complete symmetry of the information matrix. And we know if we take the complete symmetry and we add on maximal trace, that we're going to get the universal optimality from Kiefer's result. The weighted case, it doesn't work out this way. This generalized group divisible form is the maximal symmetry we can get, but the trace maximization turns out not to be playing so much of a role anymore. And Kiefer-like universal optimality doesn't happen here. In fact, what we find typically is that different weighted criterion can lead to very different optimal designs. Well, whatever you want to argue about optimality criterion in the standard setting, the unweighted setting, they tend to migrate towards the same kind of design. That's not the case here, which means when you're weighting, you really need to think about the meaning of the criterion. Okay, so some optimality results. Here's a simple one for E. It says that if we can get an information matrix of this form, notice the I minus, remember that's square root of the weight vector, the constant out front. And if this design also maximizes the minimal diagonal element of the information matrix divided by weight 1 minus weight, then this design is EW optimal over the class. Okay, so kind of thing, a Kiefer-looking thing, right? But this is only EW optimality. Typically, this will not give you other types of optimality. This condition that you have a matrix of this form we call weighted balance. This is the extension of variance balance to the weighted case. What it actually says is every weighted contrast, or every contrast has the same weighted variance with the structure. You can show that if you have a binary block design, then this condition is achieved, and so corollary of this, every binary weight balanced IBD is EW optimal. Okay. So we have a number of types of ways of building designs. These look like things that are done with test treatment versus control, not surprisingly, when we look at the case with V1 equals 1. This result is nice. It says that any 2-group divisible design with one element in the group is weight balanced for some weight. And you can figure out that weight from the information matrix. And so it's going to be EW optimal for some weight. Now, is that the weight you want? That's a different question. All right? But here's a type of optimal design. Notice the weight ratio 2 to 3. Using these reinforced types of BIBDs, we could do things a little bit better, what we call weight robustness. What you really want is designs that are good for a range of weights. And so you see here weight ratios greater or equal to 3, anything like that give this, greater or equal to 5. This is EW optimal design. And maybe that weight ratio seems a little big, but it's not quite as big as that used for standard test treatment versus control, is it? Because that ratio is infinity. And by the way, infinity is included there. So just a few other things. Optimality results for completely randomized designs. Actually turns out the really hard one here is E. E I often think of as being easier, but in this case it's very hard. And it has a break point. If you have a weight greater than or equal to 1/2, then you can only allocate n-halves units to the corresponding treatment, no matter how big that weight is. If all of them are less than 1/2, then you allocate proportionally. This is continuous theory, by the way. We have also the result for the discrete case, which is very interesting because it ends up skipping large chunks of where you might think designs would be. So the discrete theory doesn't move continuously in the integer sense. But I don't have time to show that, as Angela says. So I'm going to skip right down here. We have results here for A and MV as well for completely randomized design. And I just wanted to show you a few plots. Let's get back one. What this shows is, on the axis right here is the proportion of measurements put on the first treatment. And this is changing W1, the weight on the first treatment. And the 3 lines are for A, MV, and E. And the point of this is to show how very different the designs are from the 3 criteria as you change the weight. They all intersect right here, but what's this point? That's point 2, and we're 5 treatments, that's 1/5, or that's equal weight on all the treatments. Okay? Also, one of the lessons is A always pushes the replications closer to equal than the other criteria do. The others are actually striving more for balance. But E will take you much further in loading up the first treatment than will the other criteria. That's for 5, that's for 10, and that's for 25. You can see the compression. The E never changes, but the others are pushing more towards equal replication with larger numbers of treatments. So conclusions, experiments can be optimized for differential treatment interest through conventional optimality measures on the weighted information matrix. Different measures can lead to very different weighted optimal designs, so criterion selection is certainly important. Universal optimality generally is not achievable in the weighted case. Optimality functions of efficiency factors are what? They are weighted optimality measures with weights proportional to the replications. Okay? But optimality functions of efficiency factors are appropriate for comparing designs only within a class of fixed replication. Because when you change the replication, 2 designs with 2 different replication counts, you're changing the weights, aren't you? You're changing the weights, and that's no comparison at all. Weight balance is the extension of variance balance to arbitrary weights. The weight balance is very closely related to the weighted E criterion. And finally, as we saw, the standard test treatment versus control setup is a limiting case of the weighted approach. Okay, so that's all. There's some references.
Okay, we do have time for a couple of questions. Ben has to run for his train. So are there questions for JP?
I would think that a more natural way of thinking would be that I'm interested in some contrast more than in others, not some treatments. The ATC criterion was that I'm interested in only the comparison with the control. So you might add some more contrast. Would this lead to something similar to what you have?
Well, I think it could. Of course, I can't say for sure right this minute. I will say that, with that weight matrix, you define that weighted variance. You are including all sorts of contrast. You give every single contrast a weight. And you have to think through what those things are saying when you make that W matrix. Now, if you're going to put 0 weight on some contrast that overlap with other contrasts that don't have 0 weight, I don't think it would work out. It could be formulated this way.
This is more of a comment than a question, but I think it's an excellent idea in general to assign weights to different parameters or to different treatments. We are using it a bit in my group, looking at the more general class of nonlinear problems, where we see the possibility of assigning different weights to different parameters is a good argument for using A-optimality or A-optimality-like criteria rather than D-optimality criteria, where the weights will not influence your optimal design in any way, as you noticed during your talk. I would say I tend to interpret this weighting matrix, which in your case is diagonal, as kind of a reference covariance matrix, maybe the inverse of a such, in your parameter space. Would you agree with that? And that would also allow you to take weights to linear combinations of your treatments or parameters. And is that something you have looked at?
Not extensively, but it's quite true. We took it, I showed you diagonal here. It doesn't have to be diagonal, right? And in fact, there are some things that happen when you have two groups and one of them is bigger than one, then if all you take is diagonal, you can't get the variance of a treatment in group 1 minus a treatment in group 2 to have a bigger weight than either within group 1 or within group 2, according to what the W1 and the W2 are. And so then you need to use other kinds of weight matrices. But I thought for explaining it here, the best thing was to show diagonal.
This is the situation when W is equal to the base distance vector of W to the vector of application, the equivalent. Then it's a special case of yours, I guess.
Yes. Yes, except for if you're going to do that, you really need to keep the replication fixed. So you're not optimizing over this big class of designs. You're optimizing over
Yes.
this constrained class of designs.
So, because there's so much work done by some of the people you mentioned here.
Yeah, so like this paper right here, you know, so what I want to say is I think what they're doing is wrong because they're trying to maximize or minimize, whichever they're doing, functions of efficiency factors, and if they let the replications change, then you're changing the weights as you go, and that doesn't make much sense. I could have titled this talk, 2 Problems I Don't Understand. That was one of them. And the other thing I didn't understand was why people did test treatment versus control, and they only looked at those specified comparisons rather than thinking about sometimes I have to compare test treatments to test treatments.
So, I mean, I can give you a number of practical applications when you're only interested in comparing this.
And I'm not trying to argue that. But I can give you a number of practical applications on the other side.
Okay,
right?
well, and because of the time, I will let you argue about it later. So. Okay, before you all run off, there are a couple of announcements. But before we have the announcements, I would like to say on behalf of the participants here a couple of thank yous. A number of us have been lucky enough to be here for a few weeks for the workshop. So on behalf of those people, I'd like to thank very much Rosemary and Basha and Heiko and Dave for organizing a superb workshop. A lot of us aren't ready to go home. We'd like it to continue. So can we thank them? Second thank you is on behalf of all the conference participants. I'd like to thank Dave and Heiko for all their tremendously hard work. It's been a superb conference, and thank you very much. I believe Steve has something to say.
Just very briefly, and so as Rosemary mentioned at the beginning of the conference, this is the second DEMA conference, the first one having been in Southampton 2 years ago. And I think we ought to try to plan a third. And so I've asked a couple of people if that seems a good idea, and they agreed. So I'm just really asking if anybody is interested in being on the conference organising committee or scientific advisory committee to please let me know. or either myself or Dave know. I think Dave has been instrumental in organising both of them, and so perhaps he needs a rest. So anybody who's willing to help organise the next one, which we haven't, there's no plans, we haven't fixed a date, we have to make sure it doesn't clash with MODA, and we haven't fixed the location, although we have some ideas. So please get in touch if you have any ideas. Okay, thanks.
So yeah, thank you to Steve for that. Thank you to Angela for thanking us. Couple of quick thank yous we do need to make, and I'm sure Rosemary will tell me if I miss anyone out. I may not list everyone because there's a lot. This is the end of the 4-week program, so we do have to thank our scientific program advisors, who I think were Peter Muller, Terry Speed,
Henry Wen.
Henry.
Yeah.
Okay, yes, there we go. So we'd like to thank them very much for their input into the application sections, in particular of the whole workshop and the conference. The conference had a scientific advisory committee, which was made up of Anthony Atkinson. I think I wrote them down. There's a few. Anthony, Steve Gilmore, Catherine Challoner, David Steinberg, Sue Lewis, and Henry Wing. And although I was generally the messenger who told you whether you could do a talk or post it, it was their fault, not mine. Don't shoot the messenger. And finally, in the first week of the program, we had some really good short courses and introductory sessions on implied topics. So I'd like to thank Chris Bryan, Rainer Schwarbe, and Steve Gilmore for doing some really nice tutorials. And amongst others, I'm not going to list everyone. Again, Henry and Peter Towner talked to us about computer experiments. Terry Speed, Andy Lynch, and a few others talked to us about genetics. And Stephen Sen and Michael Krause about clinical trials. And that was all really good. So I'd like to thank all of those people first of all. So there's only 3 other sets of people to thank. It will be quick. The first is you guys for all coming, everyone giving such nice talks and presentations. That was really appreciated. Thank you, everyone. The second is the Institute staff who've done such a lot of hard work for us, particularly Tracy and Chia on the conference team, who worked really hard on organising this. And the third person you may or may not have seen during the time. The entire time we've been sat here, you'll notice using the cameras, they sometimes move around and things. There is someone, he's called Steve, he's sat in that cupboard, hopefully still. Are you there, Steve? I think it's true that the fruits of his labour will be appearing on the web in due course, so you can all relive the conference again and again and again. All right, thank you very much.